great pleasure to be here. These lectures are probably going to be a little bit more mathematical than some of the others. I mean, not necessarily at a higher level, but just with a little bit more emphasis on the mathematics. So I will be talking at first about modular forms, and then later about mock modular forms. And I think that these are an essential tool both in physics and mathematics. And before getting into the details, I want to just give you some brief sense of why these are important and the role that they play both in physics and mathematics. So one of the important things that they do is they give important constraints on two-dimensional conformal field theories, which are both an essential role in condensed matter in the analysis of phase transitions in simple systems, and also a building block for string theory. They play a crucial role in understanding the ultraviolet finiteness of string theory, and also in understanding anomaly cancellation. For example, the fact that there are two possible gauge groups in the heterotic string is directly tied to the modular invariance of the one-loop partition function in string theory. They play an important role in the counting of BPS states. That is, certain special states that preserve some supersymmetry. And closely related to this is the role that they play in understanding the entropy of black holes. This was famously understood in an important paper by Strominger and Vafa, and there have been many follow-ups to that. And one of the essential tools that showed up here was a certain kind of object, which I'll discuss later, which is a modular form, and so modular forms played an important role there. And they also appear in various applications of the ADS-CFT correspondence, and often in the physics literature, these are referred to as a kind of fairy tale expansion. The fairy here refers not to the fairies like little, things with wings that fly around, but a mathematician, I think John Fairy. And we will see a little bit, I'll try to give you an example of where fairy series show up in a calculation in mathematics. So this is just, well, I guess I could also add there are a few papers I've seen analyzing the spectrum of certain kinds of topological insulators, which are a very hot topic in condensed matter physics, which use modular forms. So there are many different places. They're sort of, I would say, beyond the standard tools of mathematics, differential equations, complex analysis, things like that. They're probably the first thing that physicists should learn after they learn the standard mathematics. They're extremely important and have many applications. And they also play an important role in modern mathematics, and I'm much less qualified to really talk about that, but I thought I would just mention a few things. So they provide an example, sort of a classical example, of a class of mathematical objects called automorphic forms. And these automorphic forms are a central ingredient in something called the Langlands program, which is, as far as I can tell, sort of a unified theory of at least some parts of mathematics, which drives much research in mathematics. You know that Fermat's last theorem is now proved, and the proof of that theorem by Andrew Wiles involved proving a certain conjecture, and that conjecture is now known as the modularity theorem. And again, it's known as the modularity theorem because it involves associating certain kinds of modular forms to elliptic curves over rational numbers. But again, modular forms are playing a central role. There are many areas in number theory where modular forms appear. For example, in the analysis of the Riemann zeta function. And they show up in moonshine, which I'll say a few words about in these lectures. Moonshine refers to connections between special sporadic finite simple groups for example, the monster, which is the largest sporadic finite simple group, and various kinds of modular forms. And I'm sure there are many more applications that could be listed here. So this provides some motivation for trying to learn about these. Being a physicist, I will tend to illustrate the mathematics with examples taken from string theory and conformal field theory and hopefully connect to some of the other lectures. But some development will be a little bit more mathematical than physics-based. I also encourage you to ask me questions if anything I say is unclear. And I'm also going to include exercises throughout the lectures. And I strongly encourage you to try them. Most of them will be fairly straightforward. A few might be a little bit more involved. But it's hard to learn anything without actually working with it yourself. And so I think by doing the exercises, you'll get a better understanding of this material. I'm also going to talk about mock modular forms, and I have a list here of a little bit of the history and some of the applications, but I think maybe I'll put that off until I talk about mock modular forms so that we can get going on things. All right, so I want to start at a very basic level. And so the first things that I'm going to discuss are some of the mathematical tools that we will need. And I think these are all familiar, but I'm going to go over them briefly anyway, just to put you in the right frame of mind, and also to give you some exercises which we will, the results of which I'll use later in some of the analysis that we do. All right, so the very first thing is a few results from complex analysis. So we'll be looking at complex valued functions. Take the complex numbers to themselves. We'll let z be x and iy in terms of its real and imaginary parts. And a function will have real and imaginary parts, which are functions of the real and imaginary parts of z. And the Cauchy-Riemann equation tell us that if these partial derivatives are equal, or if we define d by dz to be 1/2 of d by dx minus I d by dy, and d by dz bar to be 1/2 d by dx plus I d by dy, then this is equivalent to saying that df by dz bar is equal to 0. Then we'll say that f is a holomorphic function. And you should think of that as just depending on z, not depending on z bar. And one of the most important theorems for a holomorphic function is that if f is holomorphic, except at some points a1 up to an, then if you encircle those points with a contour C that goes around the points in a counterclockwise direction, then the line integral of f around that contour is equal to 2 pi I times the sum of the residues at f at each one of those points. And the residue of f at a point ak is the coefficient c minus 1 in the Laurent expansion of f about that point. And we're going to use this Cauchy residue formula many times in the analysis that we do. There's one more important result which we will use several times to determine that certain functions are equal to each other. And that is that you have a function which is holomorphic. That implies that it is analytic, which means that you can write an expansion about some point which converges. And we will also use the fact that if we have a bounded holomorphic function, that such a function has to be constant. And we'll use this by sometimes showing that a certain function is holomorphic. We'll show that it's bounded. And if we can determine its value at some point, we've determined its value everywhere since it's a constant. So we'll sometimes use it to show that a function is 0 by showing that it's bounded, it never blows up any place, that it's holomorphic, and that it's 0 at infinity, which means that it has to be 0 everywhere. All right, so those are essentially the results in complex analysis that we'll use. We'll use some simple results in Fourier analysis. And I'm going to be using the following convention. So if we have some function from the real numbers to the complex numbers, we will define its Fourier transform to be the integral from minus infinity to plus infinity f of x times e to the minus 2 pi I kx dx. And it's worth noting that this is a convention which is usually used in the mathematical literature. In the physics literature, you sometimes or usually don't see a 2 pi here, and sometimes there are 1 over square roots of 2 pi here. But I'm not going to do that. I'm going to stick to this convention. I will also write the form as a kind of calligraphic F, which I'm not sure I have the right font for, but so I'll sometimes write it like that. And it's easy to check that if you apply the Fourier transform twice, that you get f of minus x back. And that implies that if you do the Fourier transform 4 times, that you get the identity. Now, the reason I'm mentioning this is because we're going to encounter functions which are their own Fourier transform. And the fact that the 4th power of the Fourier transform is equal to 1 tells us we have some f such that it is its own Fourier transform up to some constant lambda, that is, it's an eigenvalue of the Fourier transform. This tells us that lambda to the 4th has to be 1, so lambda can either be 1 minus 1 I or minus I. So one example, should be familiar, and that is that if I take a function f of x, which is a Gaussian, and I'll take it to be a Gaussian with the normalization, which is chosen specially to make what I want to say true, then we simply calculate the Fourier transform. This is a standard Gaussian integral, which I do by just completing the square and then doing the Gaussian integral, and gives e to the minus pi k squared. So the Fourier transform of a Gaussian is a Gaussian, a fact which should be familiar. And if I normalize the Gaussian in this particular way, then I get the function back again exactly. Sorry? Yeah, I mean the pi here. So the width of the Gaussian is chosen so that I get that width back again. And obviously you could choose a different normalization. And so here's the first exercise. So the first exercise is to let f tau be e to the pi I tau x squared, with tau an imaginary number such that the imaginary part of tau is positive. And the exercise is to show that the Fourier transform of this Gaussian with a different factor is the square root of minus I tau times f of minus 1 over tau. And that is a simple exercise, just using that integral and doing a simple change of variables. Here's another exercise. It's a little bit more involved, but not too bad. And this is a result which we're not going to use until somewhat later when we encounter mock modular forms. And you may not have encountered before. So let g of x be 1 over cosh pi x. This function is also its own Fourier transform. So by considering the following integral, where the contour is as follows. So here is the z-plane, and consider a contour that runs along the real line to some value m, and from minus m, that then goes up and back over, with this point here being I, this is the origin, and then goes like this and back down, and then take the limit as m goes to infinity. So you're supposed to consider this integral along this contour as the boundaries of the contour go off to infinity, and use that to show that the Fourier transform of this function g gives the same function back. Now, I don't know about you, but I mean, the fact that the Fourier transform of a Gaussian is something that you often encounter when you learn quantum mechanics and study the simple harmonic oscillator, because the ground state of the harmonic oscillator is a Gaussian. This fact seems kind of odd. I mean, I don't think generally, unless you've solved some particular potential problems in quantum mechanics, you generally encounter this fact. And it makes you wonder, well, how general is it? I mean, are functions that are their own Fourier transform very special? Do they occur all over the place? What if I wanted eigenvalue I or minus I instead of 1? And so let me just, this is not exactly a problem, but just something that you might want to think about, or it could be turned into an exercise, I guess. So let's consider the simple harmonic oscillator. So after some rescaling, or choosing your constants to be, 1, so forgetting about 2m's and omegas and all that, the harmonic oscillator Hamiltonian is p squared plus x squared, where these are now operators. And we have commutation relations that the momentum with x is equal to minus I times h bar, but I'm putting h bar equal to 1. And if I consider a transformation which takes p to x and x hat to minus p hat, this transformation leaves h invariant, and it leaves the commutation relations invariant. So this transformation, which takes coordinates to momenta, coordinate space to momentum space, is a symmetry of the simple harmonic oscillator, which is essentially the Fourier transform, going from coordinate space to momentum space. So that suggests that one way of understanding functions which are eigenfunctions of the Fourier transform is by looking at eigenfunctions of the simple harmonic oscillator, because since this commutes with the Hamiltonian, you should be able to find eigenfunctions of both the Hamiltonian, energy eigenfunctions, and eigenfunctions of the Fourier transform. And so I guess if you want, you could consider the following exercise, 3. Let's consider the coordinate space eigenfunctions of the simple harmonic oscillator, that is, eigenfunctions such that h on these gives us n plus a half psi n. Again, here I've taken h bar omega to be 1 in some units. Show that the Fourier transform of the nth eigenfunction is equal to minus I to the n times psi n of x. So in other words, the energy eigenfunctions of a simple harmonic oscillator, which involve Hermite polynomials times Gaussians, provide you with an infinite set of eigenfunctions of the Fourier transform. And since the energy eigenfunctions of the harmonic oscillator are a basis for square integrable functions, we can write any function which is an eigenfunction of the Fourier transform as combinations of the psi n of x, the harmonic oscillator ground states, or sorry, harmonic oscillator eigenstates. All right, the next tool that we're going to use is something that's absolutely essential in understanding modular forms, which is Poisson summation. So let g of x be a function of the real numbers with sufficiently fast fall off as you go to plus or minus infinity, such that if you define a function f of x to be the sum of the function g at x shifted by an integer n, and you sum that over all integers, this sum should be convergent. So I'm not going to try to say exactly what the conditions are, but obviously if this function falls off exponentially or falls off as a high enough power of 1 over x, then this sum will be convergent by the usual tests for convergence of sums. So we want that to be convergent. Okay, so if that is the case, then you can show that the sum from minus infinity to plus infinity of the function g evaluated at integer points is the same as the sum of its Fourier transform evaluated at integer points. And this formula is the statement of Poisson summation. that a sum of a function at integer points is equal to the sum of its Fourier transform at integer points, provided that the function g falls off sufficiently fast that this sum converges. And the proof of this is really not difficult at all, so I'll show you how it works. And we are going to use this many times in what follows. So the proof, well, let's first of all note that f of x is a periodic function with period 1. So in other words, f of x plus r is equal to f of x for r an integer. That's kind of obvious because if I just shift x by an integer, this sum is still the sum. It still sums g of x plus an integer shift over all integers. And so changing x by an integer doesn't change the form of that sum. And since f is a periodic function with period 1, we can write a Fourier series for it. So the fact that it's periodic means that it has a Fourier expansion. In terms of a basis of periodic functions with period 1, that is just the exponentials or cosines and sines. And by the usual way that Fourier analysis works, the coefficients are given by this integral, which you can see by just plugging this in and then using the standard delta function orthogonality relations for the exponentials. Okay, but we now can use the definition of f. So these coefficients are the integral from 0 to 1, but the function f itself is a sum of g shifted by integer points and here, by changing variables an infinite number of times, I can make the sum from 0 to 1 dx be an integral from minus infinity by defining x prime to be x plus n over each interval and then stringing together the integrals. So this is equal to the integral from minus infinity to plus infinity, g of x e to the minus 2 pi I mx dx. Okay, well now we look at the function f evaluated at 0. So on the one hand, from the definition of f, this is equal to the sum on n, g of n, since we've just evaluated g of n plus x at x equal to 0. But on the other hand, the coefficients Cm from this formula are simply the Fourier transform of g evaluated at m. And if I evaluate f of x at x equals 0 from this formula, I get this. This is the sum on m equals minus infinity to plus infinity times the coefficient Cm, but the coefficient Cm was just the Fourier transform of g tilde of m. So that's the statement that we wanted to prove of Poisson summation. All right, so let me pause for a moment and ask if there are any questions. I would also encourage you to make comments, because I am happy to try to adjust what I'm saying to fit the audience, which means I can go slower, I can go faster. If I'm going too fast, or if I'm speaking too quickly or writing too quickly, you should say something, because if you don't correct me now, you're going to have to sit through many more hours of my bad behavior. So if there are things that you would like to suggest that I do differently, now is the time to speak up. Yes?
Could you explain again the step when you define x prime and equal x plus n?
Sure. Sure. So let's look at this formula. So we have the integral from 0 to 1, sum n equals minus infinity to plus infinity let me exchange the order here. And, well, let me just write out a few terms. So a bunch of terms. Let's pick out the term with n equals minus 1. So there's an integral 0 to 1 g of x minus 1 e to the minus 2 pi I mx dx, plus integral from 0 to 1 g of x e to the minus 2 pi I mx dx, plus the integral 0 to 1 g of x plus 1 plus an infinite set of terms. So I've picked out sort of the middle three terms in this infinite sum. So now let's look at these. In the first integral there, let me set x prime equal to x minus 1. So I then have the integral, so x goes from 0 to 1, so x prime goes from minus 1 to 0, and then I have g of x prime e to the minus 2 pi I m, and x is x prime plus 1 dx prime. But the plus 1 here doesn't do anything because m is an integer, so I can erase this. And so I have this integral, but now from minus 1 to 0. For the other term, I can just let x prime equals x. I can let x prime equals x plus 1. The last term where I let x prime equals x plus 1 is going to give me an integral. X went from 0 to 1, so x prime goes from 1 to 2. And then I have g of x prime e to the minus 2 pi I mx prime. And so on. In the nth term, I let x prime equals x plus n. The exponential doesn't change when I make that change a variable. And I just get integrals from minus infinity plus 1, until I get a set of integrals from minus infinity to plus infinity. Yeah.
There was a remark you made earlier about automorphic implies analytic.
Right.
And something about the series starting from 0 to 1.
Right.
Could you say that?
So a function is analytic a function is analytic at a point, let's say A in the complex plane, if it has a convergent power series expansion in some neighborhood of A. So if I can write f of z as a sum n equals 0 to infinity, some coefficients z minus a, let's say, to the n, and this series is convergent, then this expansion defines the function in some finite neighborhood of this point A. And so you say a function is analytic at A if it has such a convergent power series expansion. And you would say that it's just analytic period if you had a convergent expansion in the whole complex plane. And it's a non-trivial theorem, which I'm not going to prove. I don't think it's that hard, but anyway, it's not. Would be more pure math than we want. That says if a function is holomorphic, then it's analytic. Other questions? Okay. The theorem that holomorphic implies analytic? I don't know if it has a name associated with it or not. Yeah, I'm not sure. All right. So, let me write down the first example of a modular function. And I kind of went back and forth over how to do this. And let me just try to explain why and hopefully help you understand why I'm doing things the way I'm doing it. So I'm not going to define precisely what a modular function is yet. In the next couple of lectures, I will give you precise mathematical definitions, and we'll see what sort of objects obey those definitions. But physicists often call things modular functions without being very specific about exactly what that means, and usually get away with it. But there are times when a little more precision is needed, either because you encounter some subtlety that you hadn't realized, or you're trying to talk to a mathematician, and the mathematicians don't necessarily need precision, but they want definitions. I mean, they want to know exactly what you're talking about. And the other reason is that the object that I'm going to tell you about, to start out with, which is called the Jacobi theta function, is, first of all, I think, historically, either one of the earliest modular type objects, or maybe is the earliest. I think it goes back to work in the 1800s. And secondly, it provides a very useful template for various objects that we will be discussing. So in particular, as we go on, we'll talk about elliptic functions, modular forms, Jacobi forms, and this theta function is kind of a useful template for discussing all of them. I think it was a motivation for much of the development of modular forms. So let me tell you what it is, and then I'll tell you some of its properties in mathematics, and I'll explain or give you as problems some examples of how it arises in physics. And we'll also see how it arises in conformal field theory and string theory in various places. So I'll define it by an expansion, power series expansion, q to the n squared over 2, y to the n. And here, and I think throughout these lectures, every time you see the variable q, it really stands for e to the 2 pi I tau, with tau a complex number with the imaginary part of tau positive, and we will write that as tau is in H, where H stands for, in the complex tau plane, the part of the tau plane with the imaginary part of tau greater than 0, that is the upper half plane. And y will be e to the 2 pi I z, and z is any complex number. So the first thing to notice is, since the imaginary part of tau is positive, q is less than 1, and so this sum will converge and define some function of tau in z, where tau is in the upper half plane and z is a complex number. Of this function under certain transformations of the variable z and of tau. We'll see that these transformations have a group theoretical significance, and I'll explain in physics and conformal field theory where that group theoretical significance comes from. But first, let's just derive what the properties are. Okay, so the first thing to note is the easiest. If I shift z by an integer, theta doesn't change. Well, that's just because if I shift z by an integer, y doesn't change, and theta only involves y. So that's kind of obvious. There's a less obvious property, which is if I shift z by tau, I also get a fairly simple transformation. So let's just work out what that is. So I shift z by tau. I'm writing out explicitly what q and y are, so there I've just shifted z by tau. And now I can rewrite this as follows, kind of skipping a step, but I think I'll explain what I'm doing here. All right, so I claim that these two things are equal. So, all right, here's an e to the 2 pi I n z. I've added a 1 here, but then I've taken out e to the minus 2 pi I z. So this term cancels this term. Right, so that matches that. Now, there's an e to the 2 pi I n tau. I've put that into this formula by the cross term when I expand n plus 1 squared. This n squared over 2 tau term is the first term here when I expand this. And then there's a term that involves e to the 2 pi I tau over 2, and I've canceled that off with this term. Okay, so that's correct. And now the reason for doing this, well, the sum on all integers n plus 1 is the same as summing over all integers n. So this is equal to e to the minus 2 pi I z minus pi I tau times theta of z, and tau. And if you want, it's easy to see from these two facts that if I shift z by a plus b tau, where a and b are integers, that I simply get e to the minus 2 pi I bz minus pi I b squared tau times theta of z and tau. Shifting by an integer doesn't do anything. Shifting by an integer times tau just gives me this factor back b times. So these two transformation, or this one transformation law, which summarizes the other two, means the following. So in the complex plane, I have the possibility to shift z by an integer. So here's 1, 2, 3, here's the origin, minus 1, etc. So I have a periodicity under shifts by integer amounts along the real axis. And then I have a complex number tau, which has a positive imaginary part. So here's tau. And here I'm looking at the transformations where I shift the real part by an integer, or I shift by an integer plus an integer times tau. So that means I'm looking at the transformations where I shift by any point on a lattice that is generated by shifts by 1 and shifts by tau. So in other words, we have a two-dimensional lattice, which I will write as z plus z tau, which simply means I'm allowed to take any integer plus any integer times tau, any linear combination with integer coefficients of these two basis vectors. And when I shift along this direction, the function comes back to itself. But when I shift up, it comes back up to a phase. We can also associate to this lattice a surface where we take points in the complex plane and identify opposite sides. So if I take one of these unit cells and I identify the opposite sides, this is a two-dimensional torus, a torus T2, or a mathematician would call this an elliptic curve. And we have a function that kind of wants to sit on here, but it doesn't sit here completely because it's not actually invariant when I shift by the lattice vectors. So we'll talk about this more. I don't want to get into subtleties like this yet, but what this theta function really is a section of a line bundle over E tau, meaning that it comes back up to a phase when you shift by a lattice vector. But this group is going to play a role. So in other words, there is a group which is just two copies of the integers, which is the group generated by shifts by integers and integers times tau. So this is just an abelian group, which is isomorphic to two copies of the integers, and that abelian group is going to play a role in what follows. Sorry? Well, I haven't really defined what a section of a line bundle is. So if I wanted a function that was really defined on this quotient, then I would want a function that was completely periodic. But it's not periodic. When you go around in this direction, you come back to the same function up to a phase. So a function that comes back up to a phase you can think of as defining a line bundle, which means you have your space, and at every point in the space you've got a phase, a complex number of magnitude 1, and you have to patch things together with transition functions as you go from one region of the space to the other region of the space. So this rule tells you how to patch together the theta function as you go in the tau direction. So that makes it a section of a line bundle, even though I don't want to define exactly what that is right now. Okay, so far we've seen that there's a transformation law when we change z, which has a group theoretical significance. But there are also properties when I change tau. So there are interesting tau transformations. And I'm going to analyze those first by setting z equals to 0. And for z non-zero, I'm going to give you an exercise. So let me look at this theta function at z equals 0. So again, one thing is kind of simple, and the other part is a little more complicated. So if I shift tau by an integer, I don't quite come back to myself, because when n is odd, its square will be odd, and shifting tau by an integer would pick up minus 1 to the n. But if I shift tau by 2, then I always have 2 pi I times an integer, and so that leaves the theta function invariant. Now, the other transformation, however, is very non-trivial and quite interesting, and it has to do with the transformation when I take tau to minus 1 over tau. So to evaluate this theta function at minus 1 over tau, I appeal to the first exercise and our formula for Poisson summation. So consider the function, well, I don't know, I'm running out of names for functions, but anyway, let me let h of tau be e to the pi I tau x squared. I guess this is probably what I called f sub tau earlier, but anyway. Let me just call it g of x, because that's what I used in the Poisson summation. All right, so the sum of g of n is simply our Jacobi theta function at z equals 0, but the sum of its Fourier transform at integer values is, by the first exercise, 1 over the square root of minus I tau times e to the minus pi I n squared over tau. Remember, because the exercise was to show that this function has a Fourier transform, which is this factor of 1 over square root of minus I tau times the function at minus 1 over tau, which is what this is. But this is 1 over the square root of minus I tau times the Jacobi theta function at 0 and minus 1 over tau. All right, so we have square root of minus I tau. So I will give you a group theoretical interpretation of this somewhat later, but these transformations are not, well, they're connected to a group called the modular group, but we're not going to get to the modular group for a little while, so I'm going to postpone that. Okay, now I promised you some connection to physics, and the first connection to physics is actually, I believe, the historical way in which this Jacobi theta function appeared. So consider the heat equation that tells you how temperature diffuses with time in one dimension. So this is an equation for a temperature, T, that depends on time and depends on one spatial coordinate. I mean, it's not very realistic physically because we don't have too many things that are exactly one-dimensional, but you know, if you had a very long, thin rod, this wouldn't be too bad an approximation. So the heat equation says that the change of temperature with respect to time is equal to alpha times the second partial derivative with respect to space of the temperature, and alpha is the thermal diffusivity. So here's another exercise. I think I've lost track of the numbering. But do this on a line segment. X is between 0 and L with periodic boundary conditions that the temperature is periodic with period L, or it's the same at the beginning, at the end. So in other words, we have our system where this is 0, and this is L, and this is X. And if we use periodic boundary conditions, that's the same thing as I'm really working on a circle with the circumference being L. And if the temperature at time t equals 0, if t at L over 2. So in other words, I consider an initial temperature profile which has a delta function peak at L over 2. Well, we know that when you solve a differential equation with a delta function source, that gives you a Green's function. So find the temperature T and express the answer in terms of the Jacobi theta function, theta of z and tau. Or, if you prefer, consider quantum mechanics on a circle and take phi to be identified with phi plus 2 pi. The Hamiltonian, if it's a free particle on a circle, is just minus h bar squared over 2mr squared times d squared by d phi squared. Wave functions should be periodic. And compute the thermal partition function z of beta, which is trace e to the minus beta h, which tells us the finite temperature behavior of this simple quantum mechanical system, which is just a free particle moving on a circle of radius r. So if you really want a nice exercise, do this computation using canonical methods. By canonical methods, I just mean, the usual analysis. You know exactly what the eigenstates are of this very simple Hamiltonian and write down the sum. Or B, using path integrals. This is one of the simplest sort of non-trivial path integrals you can do in quantum mechanics. It's just a free system. There's no potential. It just has a kinetic energy term. But you have to keep track of the fact that paths can wind around the circle when you sum over all paths. And what you'll find if you carry out this exercise is that you can express this in terms of theta of tau, and you can express the path integral result in terms of theta of minus 1 over tau. And the fact that the path integral and canonical methods should agree is simply this modular transformation property of the theta function. So if you want, this is a physicist's proof of this relationship for the theta function, but mathematicians would not regard that as a proof because they don't think path integrals exist, so how could it be a proof? But anyway, this is it's a nice, slightly complicated but not too bad exercise. Um, 2 hours is a very long time to talk, and it's also a very long time to sit and try and concentrate. Really long, I think. So what I propose to do is to take a little break in the middle of most of the lectures that I give on the order of, say, 10 minutes, which gives you enough time to, do some deep breathing, get an espresso, whatever was required to reconstitute yourself. So why don't we reconvene in 10 minutes, so 10:02 by that clock. Please. All right, good. All right, so here's our Jacobi theta function. And it's clear from this if I do things correctly, that the tau derivative of theta is equal to minus I over 4 pi times the second z derivative. Or you could also write this as d by d theta with respect to t of z and tau equal to it is equal to 1 over 4 pi d squared theta by dz squared of z and it. So the two different ways that I mentioned of seeing the theta function as a solution of the heat equation or a solution of the Schrodinger equation in one dimension is just follows from this fact that follows from the definition that it obeys a differential equation which is first order in time derivatives and second order in z derivatives. And you can either view this as the Schrodinger equation or as the heat equation, depending on whether you think of the variable tau as being real or imaginary. It should still, I mean, for the sum to converge, it should have a small imaginary part. So in quantum mechanics, what that really means is you're doing a little bit of Wick rotation to make the sum converge, but that's this thing that we're very used to doing, either giving a small imaginary part to the Hamiltonian or Wick rotating the time a little bit away from the real axis. Now, in physics, in conformal field theory, in string theory, we often encounter some of the structure that we saw in analyzing the transformation laws of the theta function. So, for example, in string theory, the perturbative expansion, which I think you're learning about in other lectures, involves, if you want to say study the scattering of string theory, in principle it involves doing a sum over the Riemann surfaces of increasing genus, where you compute correlation functions of operators in a two-dimensional conformal field theory. And which two-dimensional conformal field theory depends on exactly which string theory you're talking about, what background of string theory you're talking about. But perturbative string theory is about computing these sorts of things. And if you focus on the one loop contribution, which we call the partition function, then the Riemann surface is a torus, a T2. And a two torus also arises even if you're not doing string theory, but you're interested in conformal field theory. So in conformal field theory, in two dimensions, we often start with a system on a line Might even start with some kind of a spin system and then take a continuum limit. And if we impose periodic boundary conditions, then we're basically working on a circle. And if we compute the partition function, in the path integral formalism, this is a path integral over some set of fields in Euclidean time which are periodic with period beta. So also in conformal field theory, when we compute the partition function, which determines the thermal behavior of the system, we're essentially working on a product of two circles, which again is a two torus. So in conformal field theory, in string theory you need to do more computations, but one of the important ones is understanding what happens when you compute correlation functions on a two torus. In a conformal field theory, the partition function, which has much of the information about the spectrum of the theory, involves a two torus. And so there's a very general kind of structure that one encounters. So if we have a theory which is conformally invariant on a two torus, then we can use a mathematical result which is that any metric on the two torus is conformal to the flat metric. And if we have a theory which is conformally invariant, then the physics won't depend on the conformal factor of the metric. And therefore, we are interested in studying the system on a two torus with a flat metric, no curvature. So a two torus with a flat metric, I can simply think of that two torus as taking the complex plane and modding out by some two-dimensional lattice. Now we saw something like this just a little bit ago, but now I want to be more generic because I'm not making any assumptions other than we can view the two torus this way. So in particular, if I just have a completely generic two torus with a flat metric, I can think of that as being determined by the quotient by some lattice. Sorry, I'm not very good at drawing these lattices. I'll call this L omega 1 omega 2, which is just the lattice I get by taking integer combinations of two arbitrary complex numbers. Now, since the theory is conformally invariant, nothing can depend on the scale of the metric. And so it makes sense to do the following. Take my complex numbers omega 1 and omega 2, which determine the periodicity of this lattice, and let W, well, or maybe I'll just call it omega, or I'll try to write it as W, be a point in the complex plane modded out by this lattice. All right, so I've got this lattice, omega 1, omega 2, and I have some point in here that I'm calling W. So if I want to keep track of that information, but I don't care about the scale, then omega 1 and omega 2, of course, can't be 0 because then this lattice would degenerate. So I can choose to simply pull out a factor of omega 2 and I can also choose the imaginary part of omega 1 over omega 2 to be positive. If it wasn't, I could just change the roles of omega 1 and omega 2, or basically it's a question of choosing an orientation for that two-dimensional torus that I get by quotienting out the complex plane by the lattice, so I can always make this choice. And I will then write this as omega 2 times tau 1 and z, where now tau is just this ratio, and I've rescaled everything by pulling out a factor of omega 2. So this is just a scaling of the lattice and a scaling of the point within the lattice, and I'll call my rescaled point on the torus z. Now, we can get exactly the same lattice by choosing a different set of basis vectors. As long as I choose another set of basis vectors such that the fundamental parallelogram has the same area, then I'm just defining the same lattice but in a different basis. So if I take omega 1 and take some linear combination of my basis vectors to redefine what I mean by omega 1 and omega 2, so if I do these transformations where A, B, C, and D are integers, and I do it such that I leave the area form, d omega 1 wedge d omega 2 invariant, that implies that AD minus BC should be equal to 1. So I can ask what this transformation, that's a change of basis for the lattice, does to my rescaled ratio of lattice vectors and coordinate on the torus. And the answer is, well, tau goes to, or tau is equal to omega 1 over omega 2, and it goes to A omega 1 plus B omega 2 over C omega 1 plus D omega 2 under this transformation. But dividing by omega 2, that's just A tau plus B over C tau plus D. And Z, which labeled a point, W, rescaled by omega 2, goes to W over C omega 1 plus D omega 2. But that's Z omega 2 over this, which is simply Z over Z tau plus D. So to summarize this, we have a set of transformations where A, B, C, and D are integers with AD minus BC equal to 1. And we would expect this set of transformations to leave the partition function of a conformal field theory or the one-loop partition function of string theory invariant. It corresponds to just changing the basis of this lattice, or you can also think of it as generating diffeomorphisms of the two torus which are not connected to the identity. So for example, if you take a two torus and you slice it along one cycle and then you twist by 2 pi and reglue it, that's a diffeomorphism of the torus, but not one that you can reach from the identity by doing small transformations. So this group of transformations, A, B, C, D, integers with AD minus BC equals 1, is called the group SL to Z, meaning it has integer entries, 2 by 2 matrices, and the S means that the determinant is 1, which is this condition on AD minus BC. So the first part of this, that we have a set of transformations on tau, is saying that we have an action of the group SL to Z on the upper half plane H, and points in the upper half plane, tau, modulo this action of SL to Z, label conformal equivalence classes of two tori, or elliptic curves E tau. So for each point in the upper half plane, modulo the action of SL2Z, I get a two torus, which is distinct from any other two torus up to doing conformal rescalings of the metric. So for this reason, tau is called a modulus. And the group SL2Z is often called the modular group. And I guess you could say this is kind of one of the simplest examples of a situation which occurs in string theory compactifications, which is you often have some set of spaces, like a Calabi-Yau space, that has some moduli that label different points within some topological class of spaces. And those things manifest themselves in string theory often as, with unbroken supersymmetry, as massless scalar fields. This is one of the simplest examples of a modulus. Here we have something that's a modulus for just the two torus. There are a few facts about the modular group which I'm going to just state without proving. One well, okay, first of all, I guess I want to say something that's really kind of simple. So first of all, let's note that in terms of the action on tau, the group element, which is the identity, and minus the identity act the same, because I'm looking at these fractional linear transformations. And so if I change the signs of A, B, C, and D, I don't change the sign of this transformation. So it's often useful to work with a slightly different group, which is called PSL2Z, which is SL2Z modulo 1 and minus 1. So you regard the identity and minus the identity as the same element in PSL2Z. But you have to be a little bit careful, which is if you include the action on Z, which is a point on this 2 torus, then you really ought to work with SL2Z, because the transformation on Z does depend on the sign. Okay, so I can say just a little bit more specifically now what I was referring to earlier. So there's a demand that the one loop partition function of string theory or conformal field theory should be modular invariant. Meaning invariant under these transformations of SL2Z. And it's this constraint under actions of SL2Z that are responsible for some of the things I mentioned earlier, anomaly cancellation, work of Cardy's that constrains the spectrum of conformal field theories and such. And I'll say a little bit more about this later. So, although the theta function didn't quite fit this description, we can extract from the kinds of this sort of argument and the transformation laws of the Jacobi theta function the following general sort of situation. We have a set of transformations which are called elliptic transformations. And these are transformations that are taking a point on our standard 2 torus, Z, and shifting it by some combination of lattice vectors over to a point, equivalent points in this lattice. And this transformation depends on a parameter tau, which specifies this 2 torus or elliptic curve, which is this quotient of the complex plane. And these form a group. The group here is just 2 copies of the integers, because mu and lambda here are integer. But we've also seen that we have modular transformations. Which take tau to a tau plus b over c tau plus d, and take z to z over c tau plus d. And here, the group is SL2z, or PSL2z if I ignore the action on z. And if we wanted to be completely general, we could consider combining these two sets of transformations. And these combined transformations are transformations of something called the Jacobi group. So we have elliptic transformations, we have modular transformations, and if we want to combine them all, we have things that are called Jacobi transformations. And corresponding to each of these possibilities, yeah. Because taking z and identifying it with respect to this action defines for me a 2 torus, but this is also called an elliptic curve. And I'm not really talking about the algebraic geometry of such things, but you can define certain curves by cubic equations that are called elliptic curves, which are essentially these objects. So the word elliptic refers to the nomenclature that this is an elliptic curve. So, yeah. Sorry? Well, it's just, so the group consists of transformate by shifts by 1, 2, 3, etc., and shifts by tau, 2 tau, and all combinations of them. So that's just 2 independent translations, and the group of translations is just isomorphic to the group of integers with addition of integers. So it's Z2 because I have 2 copies of the integers, 2 independent translations. So, you know, I'm regarding on the real number line with integers 0, 1, 2, -1, -2, I'm regarding the set of all integers as a group and writing it as Z, where the group elements are just addition, where the group is addition. And I have 2 copies of that because I have translations in 2 independent directions. Okay, so we can, if we think back to the Jacobi theta function, it had fairly nice transformation properties under these elliptic transformations. It didn't quite work under all of the modular transformations because you can see that the modular transformations include just tau goes to tau plus 1, and that was not that did not leave the Jacobi theta function invariant. So in a way, the Jacobi theta function is not a perfect example of this, but we can ask ourselves, can we make some other set of functions which are either invariant or transform nicely, we'll have to say what that means, under E, the set of elliptic transformations, M, the set of modular transformations, or J, the set of Jacobi transformations. So the Jacobi theta function was something which had some kind of mix of these. We'll have to specify what it had. But we could just consider the question of, what if I just consider these transformations separately? And I don't know the exact history, but I think some of the history of the development of this field must have involved abstracting away from the Jacobi theta function certain properties and asking whether you could define functions that just had that property separately. You know, in the way that mathematicians like to take some property and make it more abstract and general and figure out what to do with it. And the answer is yes. You can consider things that are invariant under elliptic transformations, and these things are called elliptic functions. But elliptic functions secretly, or not so secretly, depend on a parameter tau, which labels an elliptic curve or a two-torus. And so consideration of these naturally lead to things that have nice transformations under modular properties, and that leads to modular functions, which you could discuss separately from elliptic functions, but they're kind of linked. And then there are things called Jacobi forms, which combine both the modular and elliptic properties. So there's kind of a hierarchy here of functions with transformation laws under certain groups that we can discuss. And for Jacobi forms, there turn out to be at least two interesting cases, depending on exactly what properties we want. There are things called holomorphic Jacobi forms, and there are other things called skew holomorphic Jacobi forms. Yeah.
For the modular forms, the interest is because we are trying to preserve the area of these lattice, and it's interesting because of the partition functions that we're looking at. But the elliptic transformation, what's the motivation?
Well, just because it's something we could think about. We'll see that once we define elliptic functions, modular functions follow. So once I define this, the modular functions will really pop out. So at least my motivation for starting with elliptic functions is because it's a very natural way of introducing a certain set of modular functions. I guess I could present things without ever talking about elliptic functions, but it seems a little artificial to me mathematically to not talk about them. The Jacobi forms, we will see, are related to something called the elliptic genus of Calabi-Yau spaces or of a conformal field theory, and they play a very important role in counting BPS states, computing the entropy of black holes, and they show up in various kinds of moonshine. And I'm going to stop in just a minute, but let me just say one thing, which is probably one of the most important ideas in this whole subject, and one that I'm going to develop in a lot of detail in the next lecture, and that is the following idea. In each of these cases, we have a group G which acts on Z or tau or the combination of Z and tau. And we will try to construct functions of Z or tau or Z and tau that either are invariant or transform nicely by the procedure of averaging over G. So we'll take the function, we'll take some simple function, and we'll average it by computing its transformation under all the group elements. So if I take some function and, well, just sort of abstractly, I take, gf plus g squared f plus, I average it over all the group elements. Several things can happen. One is you could just get 0. If I try to take a vector and I average it over all rotations of the vector, I would just get 0. You could get a nice function which is invariant. Or the sum over all the transformations could diverge. We'll see that when the sum diverges, we ought to do what any good physicist would do, is we should try to regularize the divergence in some way and see if the properties that we want are maintained when we regularize it. And we'll see that to some degree that's possible. So really this idea of averaging over a group is very general and can be applied to many of these cases. And over the next few lectures, I'll apply it to give you a different way of thinking about trigonometric functions. We'll use it to construct elliptic functions. We'll use it to construct modular functions. And if I have time towards the end, we'll use it to try to construct certain things called Rademacher series, which play a role in some speculations about ADS3 and things related to moonshine and all sorts of fun things. But this idea of averaging over a group has many, many applications and is one of the main things that I want to get across to you. And so we'll do a bunch of that in the next lecture to construct elliptic functions, modular functions, trig functions, and study some of their properties. Okay, so that's it for today. I'm happy to answer questions, but I'm also going to be here for lunch, so you can ask me questions over lunch too.